Hello there, I'm J.M. Vyshevsky, and I lead the research and development here at MindsApplied. I'm extremely excited to share a demo of a new technology we've created called the MindsAI Filter for EEG. The filter is a part of a suite of tools from our MindsApplied Artificial Intelligence research. This is a simple-to-implement filter that relies on sensor fusion to recognize the physics of true brain activity and in turn remove artifacts and suppress noise. It takes time series data in the standard format of channels x time points and requires no configuration except the lambda hyperparameter, which can be easily adjusted to tailor the strength of the filter to your needs. Now, why should you care? There's quite a few other filters out there, ICA, PCA, ASR, and they all have their strengths. They also come with trade-offs and require expertise in signal processing and programming. PCA assumes you know what the true neural signal looks like and that artifacts stay stable across sessions. ICA is difficult to work in real time because it requires extra steps to classify components of the signal as clean or noisy. Finally, ASR depends on finding clean stretches of data, which may not always be possible. The reality is, artifacts and noise shift dynamically across devices, tasks, and individuals. Relying on these assumptions risks removing valuable information or missing unexpected but important influences from the signal. This is where your MindsAI filter excels. The filter adapts to changing conditions, can perform offline or in real time, and outperforms every other state-of-the-art method across whole brain data. If, like us, you're building applications for inner speech, motor imagery, or emotion recognition, your MindsAI filter is the obvious choice. Don't believe me? Our results and comparisons are available at minds-applied.com/mindsai. Want to test for yourself? We built you an app for signal visualization and metrics, all available today. This is a demo app script for real-time analysis that can be accessed on GitHub, along with comparative research results and documentation of everything I'll touch on today. An offline script for testing larger windows of data and comparing your MindsAI filter to others is available there as well. Currently, our filter works in Python and requires internet to initialize. Alternate languages and offline experience is on the horizon, but should you have specific needs, contact us and we'll help you reach your goals. The real-time application makes it easy to visualize live neural data and noise handling from any channel and all channels on average via BrainFlow. One chart displays live signal data from a singular electrode of your choice. The white waves are raw signal, the green is filtered signal, and the purple dots are removed noise. The other chart compares the average raw signal in yellow to the average filtered signal in green across all electrodes. For each window, the console displays filter and signal quality metrics, such as signal-to-noise ratio, artifact suppression, drift corrections, smoothing, and more. First, download the latest package and license from minds-applied.com. Add the MindsAI filter package to your project file and import. Then simply initialize the filter with your license key before sending data through. Then, as mentioned, pass the lambda in your data window as a 2D array to the MindsAI Python filter method, either all at once or in a loop. The filter relies on multi-channel patterns, so having more data, electrodes, and window lengths will only make it perform better. The Tailoring Lambda controls how strong the filter acts on the data. A tighter lambda is needed when less data points are available, such as during real-time trials. However, increasing electrodes, sampling rate, or window length, like during offline analysis, can usually use a weaker filter with a higher trailing number after the exponent. This is on a logarithmic scale between 0 and 0.1. So remember, the higher the trailing number is in fact a lower value. You can think of it like how you would hold a hose pulling water from a dirty basin. The tighter the hose, such as 1E20, will stop most all debris from coming through, but barely any water or insightful data will make it either. 1E50, however, will send a rush of water, but filled with debris and artifacts, preventing the filter and downstream tasks from performing as expected. The default 1E25 gives us a nice smooth water and signal flow, in this example at least. However, this lambda value will be different for every device, sampling rate, and potentially experience, so best to try a few different ones to ensure optimal quality. If you want to get more precise, you can run a hyperparametric tuning comparison algorithm for yourself. However, we'll be releasing one in the coming months, and you can always reach out to our team for support as well. This value may also change with version updates, so be sure to follow our release notes and documentation for best practices. Don't want to connect a headset? We got you. The app allows you to use synthetic data, through which noise and artifacts can be injected and highlighted. Noise can be added to all channels, like continuous 50 Hz power line noise, or to the individual channel, such as from a burst or flat line. You can also test data from a real device, like the Neurosity Crown or the OpenBCI Mark IV worn here. The Mark IV uses the Sight and Daisy board and has 16 dry electrodes with a sampling rate of 250 Hz. The Crown has a similar sampling rate but with only 8 electrodes. Yet, because the electrode placement is generally encompassing the whole brain, your MindsAI filter can still consider global activity. Our filter works with any headset, streaming time series data, but the test app is equipped for devices supported by BrainFlow. Alternative sources will need to manually code the connection or reach out to our team. Since the filter relies on global properties of brain activity, the more electrodes and greater window length, the better it performs. We'll be releasing a filter for few electrodes, like 1 to 4, in the coming months. Now returning to our demo. Of course, be sure to verify the quality of all electrode data being sent through the filter. While your MindsAI filter can adjust to a bad electrode, they can still skew your data and downstream results in unexpected ways. After initializing the filter and running the Python script from the command line, the two charts will appear visualizing signal data and metrics will show up in the command line. My assistant will demonstrate the effect of the filter dealing with various real-world artifacts and noise. Window 143.54. Okay, we're going to start with an eyebrow raise. Here, during an eyebrow raise, we can see a large burst in amplitude and noise. In this example, we use mean square power to determine the signal-to-noise ratio, or SNR. Mathematically, this makes noise power far greater than signal power, leading to a negative SNR in the console. However, in our visual, we see the green filtered line hold steady, showing that though the signal is overwhelmed with noise, the MindsAI filter is stripping the majority of it away. In the console, we also see flags thrown for this artifact suppression, baseline drift correction, and variance smoothing. Also included for further understanding is signal strength over noise percentage and bandpass information, whether it's on or off. These console flags have configurable thresholds, such as artifact suppression, which is thrown when the filter reduces a peak amp, currently and by default of 20%, drift correction, which appears when the mean or median is recentered by a default of 5 UV, and variance smoothing, which is when the filter performs a reduction in variance by 5%. SNR type can also be updated to use purely amplitude ratio, like in my next example, which contrasts absolute amplitude of the signal and noise. Or variance ratio, which compares the spread of the filtered signal to the residual noise, kind of like how much it wiggles around its average. But once again, these are purely console interpretations and will not affect the filter or visual. 242.28. We're using variance ratio now with a hyperparameter of 1E25. Here, during a head tilt, there are thousands of microvolts from motion artifacts along the white raw EEG. The green MAI filter continuously removes these spikes, shown as the dotted purple noise. So even when the SNR, which is using variance ratio, drops into the negative with artifacts being stronger than brain signal, the filter keeps the usable signal intact, showing baseline correction and variance reduction in real time. This is exactly the type of robustness you want when working with live, wearable EEG in real-world conditions. Though the live app detrends the data by default, there are no other filters being applied in this demo. However, a bandpass is optional to be configured and switched on or off at your leisure. This is a multi-sensor fusion filter, considering all data sources to filter out noise. So while we've only tested this on EEG thus far, our setup suggests potential use for alternative forms of neural data like EMG, ECG, and ECOG, but they're in our pipeline. So if you're a lab interested in partnering to improve this technology, please reach out. The MindsApplied AI Signal Filter is just one of the many cutting-edge applications we're building here at MindsApplied. If you want to learn more or stay up to date with new releases, subscribe to this account and our newsletter at minds-applied.com/contact. We're excited about this technology, but we're even more interested in what you'll build with it. So please share your projects with us over social media or our Discord at MindsApplied. The future of neurotechnology is now.